Hi, today we're going to talk about acid-base properties of salt solutions and the common ion effect. Now, when you think of dissolving a salt like sodium chloride in water, you don't normally think of getting an acidic or basic solution. And that is definitely the case with sodium chloride. You still end up with a neutral solution. But there are some salts which, when you dissolve them in water, will become slightly acidic or slightly basic. So we're going to talk about why that is. So before we do, I want to talk about some nomenclature with regards to the conjugate basis of acids. So if you have an acid that ends in IC, its conjugate base will be an anion that ends in ATE. So to give you a couple of examples, formic acid has a conjugate base that we call formate. Acetic acid has a conjugate base that we call acetate. And there are plenty more examples like sulfuric acid, sulfate, etc., etc. Now, there are also acids that end in OUS, and those are going to have conjugate bases that end in ite. Some examples are hypochlorous acid has a conjugate base that we call hypochlorite. Sulfurous acid, which is different than sulfuric, has a conjugate base that we call sulfite. So now that you have that under your belt, let's talk about how a salt can affect the pH of a solution. And so I want you to think about when we talk about ionic compounds, we always talk about having an anion and a cation. And so these two cases are based on what about the anion and what about the cation. If the anion of an ionic compound is the conjugate base of a weak acid, it will make the solution basic. If the cation of a salt is the conjugate acid of a weak base, that will make the solution acidic. So let's talk a little more about how that happens. And we're going to start with anions. Essentially what happens is the conjugate base, when it's dissolved in water, will react to form the original weak acid plus hydroxide. And that hydroxide is what makes a solution basic. So for example, if you throw sodium acetate in water, and remember the salt is going to dissociate as it dissolves, so the sodium ions will be floating around in solution. It is the acetate that will react, and the acetate will react with water to form acetic acid and hydroxide. And so the hydroxide, again, is what makes it basic. Now, what if you have a cation that's the conjugate acid of a weak base? Well, remember that the conjugate acid is a protonated form of the base. That proton can dissociate to form the original base form and H plus in solution, and the H plus is what makes the solution acidic. Most of the salts that do this are going to be ammonium salts. Ammonium is the conjugate acid of the weak base ammonia, so ammonium, after the salt dissolves and ammonium goes into solution, ammonium can dissociate to form ammonia and H+. So both cases involve equilibria, and we're going to need an equilibrium constant. And so if you have an anion that is a conjugate base of a weak acid, what you're going to do is find the Ka of that weak acid and use it to calculate the Kb of the anion. Remember that the Ka of an acid and the Kb of its conjugate base are related by the formula Ka times Kb equals Kw. For cations that are conjugate acids of weak bases, we might be able to find the Ka of the cation, but it's also possible that we could only find the Kb of the weak base, in which case you would use the Kb of the weak base to calculate the Ka of the cation. So let's talk through how to calculate pH for salt solutions. Most of these steps are going to look super familiar because they are basically weak acid, weak base equilibria. So really the only thing that should look different in the series of steps is step 1, where we have to figure out what are we using for our equilibrium constant. If your anion is a conjugate base, we'll use Kb. If your cation is a conjugate acid, we'll use Ka. And you may have to calculate it based on what information is available to you. After that, you go through the steps that we were using before of making the ice table, adding the starting concentration, filling out the rest of the ice table by putting in X for change, substituting in equilibrium concentrations to the Ka or Kb expression, whichever one is appropriate, solving for X, hopefully with a shortcut, although may not be that way, and then using your value of X to calculate either pH or pOH, depending whether you have an acidic solution or a basic solution. If you do end up calculating the pOH using X, then you have to use the equation 14 minus pOH equals pH to get your final answer. Here we have a problem where we are dissolving sodium formate in water to make a solution. Now, the first thing you should look at in this problem is the fact that what we're dissolving is sodium formate. And you see that ATE suffix and you think, oh, this must come from formic acid. Now, the other thing that people sometimes ask me about is why is it sodium formate? Why don't they just put 0.120 moles of formate in solution? Just remember that this is a salt. It has an anion and a cation. If you just put in formate, there would be a huge accumulation of negative charge because it is a negatively charged ion, and nature doesn't like large accumulations of one sort of charge. So you have to have something in there that will cancel the negative charge. In this case, it happens to be sodium, but it could really be any cation. You could have potassium formate or something. But know that when you put it into water, sodium compounds being very soluble, it is going to dissociate into sodium ions and formate ions. And so that's how we get a whole bunch of formate in solution. We are talking about the conjugate base of a weak acid. We need to find Kb. We only have our Ka for formic acid, and so we're going to use Ka times Kb equals Kw, which is 10 to the minus 14th. And let's rearrange that to solve for Kb. 10 to the minus 14th divided by Ka. So let's now plug in our Ka value of 1.7 times 10 to the minus 4th. And we get 5.88 times 10 to the minus 11th. Now that we have our Kb value, we can make our ice table. Remember, we're looking at this equilibrium between formate reacting with water to give hydroxide and formic acid. Water, being a pure liquid, we aren't going to include in our equilibrium constant, so we're also not going to include it in the ice table. So I've just put in the generic base, protonated base, which would be in this case our formic acid, and OH minus. And our starting concentration of base is 0.120 molar because we have 0.120 moles in 1 liter. Now we're going to fill out the ice table using X as change. Remember that for hydroxide we're starting with 0. That has to increase, so we're going to put the plus X on that side. The base, we're going to lose some because it's on the other side of the reaction, so that's going to be minus X. And then we can add the initial and change rows to get our equilibrium concentrations. Now we're going to substitute the equilibrium concentrations into the Ka and Kb expressions. Before we do, I'm going to assume that X is going to be very small, and that should be pretty easy to tell because if you look at the Kb, it's 5.88 times 10 to the minus 11th, which is a super small Kb, so we're really going to have a small x. So I think it's reasonable to say that the base concentration will remain about 0.120, although we will check that later. So here's our generic Kb expression. Let's plug our concentrations into that and set it equal to 5.88 times 10 to the minus 11th. And now we can solve for X. So X squared is going to equal 7.06 times 10 to the minus 12th. And then take the square root. X will be 2.66 times 10 to the minus 6th. So now we have a value for X. We can plug it into the ice table, right? Both our hydroxide concentration and our protonated base will be 2.66 times 10 to the minus 6th. the base concentration, if you subtract that from 0.120, it still rounds to 0.120. So our assumption was correct. And now we can use X to calculate the pH. Well, we have the OH minus concentration, so let's calculate the pOH first. pOH is going to be the negative log of the OH minus concentration. So we plug in our X there. We get 5.576. That's our pOH, but we want to know the pH. And so now we use pH equals 14 minus pOH. 14 minus 5.576 is 8.424. So you could see it's not super basic, but it is a slightly basic solution. And a lot of times that is what you will see in these solutions of salts that contain conjugate bases of weak acids. So now we're going to talk about a related phenomenon that we call the common ion effect, which is really just an application of Le Chatelier's principle. So I want you to think about an equilibrium between two related species. The example I have here is carbonic acid and the bicarbonate ion, which is its conjugate base. And I want you to think about what will happen if you add some bicarbonate to a system at equilibrium. Basically, Le Chatelier's principle tells us that the equilibrium will shift towards the reactants, towards the carbonic acid side. Up until now, we've been looking at problems where we say we're going to dissolve some carbonic acid in water, or we're going to dissolve some bicarbonate in water. But the common ion effect occurs when you have two related ions or two related species that you put into the same system. It's still going to be based around the same equilibrium constant. It's just that now we're going to start out with different starting concentrations in the ice table. And so let's look at an example that will help you understand what this might look like. Okay, so if you look at this problem, it's very similar to the problem we had before, in which we're dissolving 0.120 moles of sodium formate in 1 liter, but instead of dissolving it in water, we're dissolving it in a 0.050 molar formic acid solution. So we're going to have two different equilibria going on here. We have the formate from the sodium formate reacting with water to form hydroxide and formic acid, but we also have formic acid dissociating to form formate and H+, and so these are obviously related equilibria. Now, we're going to deal with these exactly the way that we dealt with all of our other acid-base equilibrium problems. Let's start with an ice table, and you could do it either way, as a base equilibrium or an acid equilibrium. I'm choosing to do this as an acid equilibrium, and you'll see as we make our ice table that it's going to be slightly different than we've done before, because before we started out with a known amount of our weak acid and then we had 0 of the other stuff. But here we don't have 0 of the other stuff. Here we have 0.120 molar of our formate, our conjugate base. So let's go ahead and fill out the ice table, starting with our change, and you'll notice that we still have plus X on the product side, and the reason we have to have plus X over there is that H plus is still 0. H plus still has nowhere to go but up, so that side is going to be the plus X. It's going to be gaining concentration, and the reactant side is going to be minus X. So we end up with 0.050 minus X for our HA concentration, 0.120 plus X for A minus concentration, and then X for H plus. Now we're going to substitute these equilibrium concentrations into our Ka or Kb expression. Here's our generic Ka expression. And before we plug these concentrations in, let's make a simplification. I'm going to say that this is about 0.120, this is about 0.050. Now, we will see if we can actually make the simplification, but for now, let's just assume we can shortcut. So let's plug that into our equilibrium expression, set it equal to our Ka value of 1.7 times 10 to the minus fourth, and then we can solve for X. We multiply through by 0.050, and then divide through to get x equals 7.08 times 10 to the minus fifth, and this being very small is going to show that yes, we could take the shortcut. What we're going to do now is use our x to calculate the pH. X equals the H plus concentration, so all we have to do is take the negative log of it, and what we get is 4.14. So the pH of the solution is 4.14, which is acidic, and so this is very different from when we were just looking at the formate solution, which was basic. So we have looked at how salts containing the conjugate base of a weak acid or the conjugate acid of a weak base can change the pH of a solution. And what we're going to do next is look at what that means for what we call buffer solutions. So that is our next video. I hope this was helpful, and I will see you again soon.